You should have watched last Wednesday's lecture, hopefully. And I talked about electric potential. Electric potential is sort of a construct, but it is related to the potential energy. It's not potential energy. It has to do with your position in an electric field. Okay? So if you have some electric field, here's some electric field E, and you're at position A, okay? No charge there. Okay, don't think about, we'll eventually put charge there, but for right now, there's no charge. You have a potential based on this position A. I don't know what it is. I don't know, we can calculate it maybe, but there's some potential. If we can decide, well, where is the zero potential? Just like when we were talking about potential energy, we decided you could put your zero potential energy point, I'm talking about gravitational potential energy. You can put that zero potential energy point wherever you want to, and you work around that zero, okay? So, sort of the same idea here. The change in potential, let's say if you're moving from point A to some point B, the change in potential is what we're typically interested in, is equal to the negative of the integral from A to B of E dot ds. Just like we did with work, that was F dot dr or whatever we had, okay? The only thing that matters is how far you move and how much of the field is in that direction of motion. That's what the dot product does for you. It gives you the component of a vector in the direction of another vector. Okay? So in moving from A to B, you sum it up. You sum up, okay, how much field did I traverse in going from A to B? All right? It's E dot ds. Okay? That's the change in potential. Then I looked at the potential due to a point charge. So for a point charge, we know what the field looks like. So I did an example where I showed how to calculate the potential due to a point charge. For a point charge, the potential is equal to KQ over R. R is the distance from that point charge. That is with everyone agreeing that the zero potential is out at the edge of the universe. It's out at infinity. So you can watch, if you haven't already, you can watch the explanation of why we chose infinity as the zero potential point. Okay? And you do have to pay attention. I'm going to put this in a box. This is for a point charge. You do have to make note of the sign. It does matter. Positive charges yield positive potentials. Negative charges yield negative potentials. So you can have a negative potential with respect to infinity, or you can have a positive potential. Okay? All right. So that's the 2-minute version of what I did on Wednesday. I looked at this delta V and an electric field, and then we developed the potential due to a point charge. Yes?
When you were talking about the point charge and the potential, you were talking about how there was a uniform field and the electric field is considered a constant. Why isn't it considered a constant on the point charge?
Okay, that's a good question. Yeah, so I should have made a distinction between moving in a constant field and a non-constant field like the point charge. Yeah, for a point charge, I'll make a positive. It doesn't have to be. Okay. Here are all the little field lines. Okay. If we want to look at the change in potential, let's go back to this. We look at the change in potential. Delta V is equal to the negative of the integral from, let's say I'm here at R sub A, that's one radius, and I move out here to R sub B. That's a different radius. You with me? So I'm going from RA to RB, and I want to calculate E dot ds. This is no longer constant. The field falls off like 1 over r squared. That E depends on the distance from the point charge. So I can't just simply pull that out of the integral like I did with uniform field, some constant field. Okay. We did the same thing with, like when we were doing the line of charge and the disk of charge, the field was changing. You know, we were calculating that integral of kq or k dq over r squared, and r was changing. So that's why we had to do the integral. Couldn't just pull E out front. Okay? So in this case, that E, you can look at the derivation on the video, but that E is changing, and that E becomes Q or KQ over R squared. Does that answer your question? Okay. Nice thing about potentials, no vectors. We got rid of the vectors. Potentials are scalars. They're numbers. All right, there's no direction to a potential, just like there's no direction for energy or potential energy. Okay? So based on this idea of potential due to a point charge, it's summable just like we had with the electric field, except with the electric field, you had to worry about the vectors. You don't have to do that here. So we'll eventually get to the point, I mean, in practice, if you're wanting to know something about the electric field in a region of space, you're typically going to measure the potential. And then I'll show you how to calculate the electric field based on knowing the potential. I'll show you how to do that eventually. Okay? So let's say you have 3 charges, Q1, Q2, and Q3. This is the distance from Q1 to the point, no charge here. This is just some point in space. R2 is the distance from Q2. R3 is the distance from Q3. Okay, if you want to know the potential at P, sum it up. KQ1 over R1 plus KQ2 over R2 plus KQ3 over R3, and as many charges as there are. Don't square R, okay? On the test, oftentimes I see students, you know, hurrying on the test, and you're doing a field problem and you're squaring all these R's. Then you get down to the potential problem and you start don't square those R's. The potential goes like 1 over R. The field goes like 1 over R squared, okay? You sum it up, and if these are negative, then you get a negative potential, okay? If they're positive and negative, I don't know, all right? Okay. Let's look at an example of this. Yeah, I better erase this. So I'll arrange some point charges, and there was a problem on the homework like this, except you had to calculate the field. I'm going to calculate the potential. Okay. So here are some charges at the corner. I'm going to make this black. These are charges. This is some point P. Okay. It's arranged in a square. This is a -5 microcoulomb. This is a 2 microcoulomb. And this is a -1 microcoulomb. And this is 20 centimeters by 20 centimeters. It's a square. Yeah, it's not too bad. What is the potential at P? So VP equals what? Well, sum it up. Just like I showed over here. You just add them up. No vectors, no components, but keep track of the SIGNs. So I'll do that now. First one, V at P is equal to K times -5 times 10 to the -6 coulombs divided by 0.2 meters, 20 centimeters. Okay. Plus this one, 2K times 2 times 10 to the -6 coulombs, and then that's along the diagonal, so that's square root of 2 times 0.2 meters. Okay. Plus the one at the bottom right, K, -1 times 10 to the -6 coulombs divided by 0.2 meters. Add them up. That's it. So let's see. I'll go ahead and do the calculation. I'll bring K out front. What is this? -2.5 times 10 to the -5 coulombs per meter. This is 7.07 times 10 to the -6. I'm doing this in my head, so somebody correct me if I'm wrong. Plus 5 times 10, not plus, minus, I'm almost messing that up, times 10 to the -6 coulombs per meter. Did I get that right? This is the one that's iffy.
No, you got the middle one right.
Okay. I got them right? Okay. All right, so add them up. This is 25 minus 5, that's -30. So I'm guessing 2.9. Okay, 2 point something. No. Yeah. That's negative, that's negative. -2 point what? 10 to the -5 coulombs per meter. okay, times K. So K is 9 times 10 to the 9 Newton meters squared per Coulomb squared times negative 2.29 times 10 to the negative 5 coulombs per meter. And that's equal to, what is that? 1.8 and then 0.3, 27, 2 point something times 10 to the 5. Negative 2 point what?
0.06.
Let's think about units. We have a Coulomb that cancels the square, so you get, and they have a meter squared that cancels that square, so you have a Newton meter per Coulomb, that's a joule per Coulomb, that's a volt. Okay. Negative 2 times 10 to the 5 volts. It's a lot of volts. Okay.
So when it's negative, in terms of voltage, what does that mean?
Well, it means that in the region that you're in, let's say here, okay, you can think of it in different ways. It means that that electric field is going to be pointing this way, okay? You're going to be going, if you move out away from the charge, you're going to be going against the field. However, a better way to think of it is, in terms of energy, V, we're going to see eventually, I'm going to get to this, the potential energy is equal to QV, just like force was equal to QE, right? So this electric potential is related to the potential energy, and you put a charge at this point, and it has some potential energy relative to infinity. Okay. So if you put a positive charge at this point with a negative potential, that's going to have a negative potential energy with respect to infinity. Okay? You're going to have to do some work to make the charge go out to infinity. If you put a negative charge here, you have a positive potential energy with respect to infinity. It's going to race out to infinity by itself. This is the tricky part about electric potentials and electric potential energies. In gravitational potential energy, we didn't have to worry about negative and positive masses, like masses that were negative and would fly off the mountain. Okay? Yeah, they always went downhill. They always went down, they always went with the field naturally. You had to do some work against the gravitational field to make them move up. Not the case with charge. With charge, you can have negative and positive potential energies based on negative and positive charges and negative and positive potentials. So we do have to do some bookkeeping. I'll talk a lot more about that in a minute, or sometime. Okay. Any other questions on this? What I want you to get out of this is it's dead simple. Just add it up. No vectors, but keep track of the SIGNs. Okay? All right. So we're going to develop a way to calculate the potential of continuous charge distributions, just like we did with continuous charge distributions and electric field. I'm going to go through this pretty quickly as far as the lead-in. Let's say you have some blob of charge. This is exactly the same thing that I did with electric field, except no vectors. I'm going to break it up into little bits of charge. Delta Q1, delta Q2, delta Q3. Out here, I'm at some point P. R1, R2, R3. Okay, so you can imagine that this thing's broken up into all these little bits of charge, or these little cubes. The potential at point P, V at P, is approximately equal to K times the sum from I equals 1 to N of delta Qi divided by Ri. Ri. Okay. I let those little cubes get smaller and smaller and smaller and smaller. I get a better approximation. Okay? V at P is equal to K times the limit as delta Q goes to 0 of the sum from I equals 1 to N of delta Qi over R sub I. That's equivalent to letting N go to infinity. Okay? Letting delta Q go to 0 is equivalent to letting N go to infinity. It's the same limit. And we all know this. I'll write V at P. V at P is equal to K times the integral of dq over R. That's it. Okay. Delta Q becomes dq. It becomes a little infinitesimal amount of charge. You sum over wherever it lives. And R is the distance from that little bit of charge to the point P. Okay. So, let's look at the disk. We can do a disk, a ring, a plane. Plane's difficult, but a rectangular plane. That's not easy. A disk is pretty easy. So here is a disk of radius r. Okay. So it's a solid disk. It has some surface charge density sigma distributed evenly throughout the disk. And I want to know what's the potential at some distance from the center of the disk, and I'll call that distance x. So same setup we had for electric field, except now we're going to calculate the potential. Okay? So a finite disk of radius capital R, a distance x above the center. What's the potential? Surface charge density sigma. Same thing that I did with electric field. I'm going to break it up into rings. Not easy for me to draw. Okay. So I'm going to break it up into these little strips of charge. All right. And we'll sum over all those little strips. This distance to the little strip, I'm going to call R prime. Okay. That means that this distance is R, right? Yeah? The distance from wherever DQ lives to the point of interest, which is up here, that's R. Okay? So I'm going to fill in the blanks for this integral. If you remember from the electric field, dq is equal to sigma times 2 pi r prime dr prime. Remember that? Maybe not. This strip has a little width dr prime. It has a length 2 pi r prime. The area, which this is an area density, the area is 2 pi r prime dr prime. Okay, that's dq. Now for r. R is equal to what? No. Yeah. You have r prime squared plus x squared. X is a constant underneath the radical, right? Because r prime squared plus x squared is r squared. Yeah. I know my drawing's not, but that's kind of a, that's a right angle. Okay. In a perspective, yeah.
Just going back to the DQ.
Yeah.
Is volume of a cylinder, it's 2 pi r times height. Is that how you're getting
The volume of a cylinder is not 2 pi r times the height, the surface area of a cylinder. Yeah. Yeah.
So that kind of...
That's the same idea, okay? You guys haven't had Calc 3 yet. Maybe, I don't know. I could do the Calc 3 version and show you really quickly why this is true, but I'm not going to do that. Think about, when you're dealing, think about, I take a pair of scissors. This is a great question. I take a pair of scissors and I cut this thing out. I cut out this little strip, okay? Follow me?
Yeah.
All right. Here it is. I bend it and I lay it flat. This distance is 2 pi r, almost. This is delta r prime. Right? Forget dr prime right now. I'm saying it's some little width delta r prime. The smaller and smaller I make delta r prime, the closer and closer I get to the actual area of this thing. Oh, this is 2 pi r prime. The closer and closer I get to the actual little area of that little strip. So if I'm able to cut it out really thin, okay, I get better and better and better at finding that bit of area. And in the limit, when you get dr prime, you actually do get the area when you sum over this, when you take this integral. Okay? What do you get if I integrate this from 0 to r? the area. Yeah? You see what I mean, Owen?
Yeah.
If I take the integral, that's what we need. That's the area of the circle, of the disk. It's a quickie, tricky way to do it. When you get to Calc 3, you'll learn how this actually, I mean, you can understand it now. It's this limiting case where you're summing over all these little tiny bits of area. Okay? You're actually using this calculus that you've learned and seeing how it actually works and where it came from. Don't tell them, but I mean the guys up there. Okay? All right. Back to this. Okay. So we got DQ. We've got R. What else do we need? Limits of integration. Well, you always integrate from, over where the charge lives. That's going to be from 0 to capital R. So V is equal to K times the integral from 0 to R of sigma 2 pi R prime dr prime divided by R prime squared plus X squared underneath the radical. Okay. I expect you to be able to get to that point. But we're going to go ahead and actually do the integral. Haven't you guys done, like in Calc 2, the disks and rings and stuff? Finding volumes and rotations and, yeah, same kind of deal here. Okay. So we have a lot of constants that we can factor out. K is sigma 2 pi and K. All right. So V is equal to sigma 2 pi K times the integral from 0 to R of R prime divided by R prime squared plus X squared dr prime. Okay. That's an easy integral, right? U substitution, however they teach it nowadays. So I'll do the integral sigma 2 pi K. This integral is R prime squared plus X squared just, yeah, that. That works, doesn't it? Differentiate this, you get 1 over this, and then you get a 2 pi. You get a 2r prime out front, but you had a 1/2 from the differentiation, and that kills the 2. Yeah, I think that works. Evaluated from 0 to R. Okay. The TI says it's right. Julian? Yeah, okay. There you go. Okay. So we'll plug in the limits of integration. You get sigma 2 pi K. And then for the upper limit, that becomes R squared plus X squared For the lower limit, you get 0 here. You get a square root of x squared, which is absolute value x. But for the way I've got it set up, I'm not worried about the absolute value. We're some positive distance x above thing, and that's it. Okay. That's the answer. That's the potential due to the disk at a distance x above the center. If you're over here, oh, big difference, different story. Okay. Let's look at some limiting cases. What happens as big R goes to infinity? Remember how we took the disk and we let it go to infinity and we said that the electric field was a constant everywhere? What happens to the potential? Hold on. Yeah, it blows up. Ah! Yeah, the potential goes infinite. Yeah, okay. Well, if you have a constant electric field everywhere and you're moving in that field, that's a infinite potential. This huge field is everywhere. And remember, those potentials are with respect to infinity. If you move along that field out to infinity, you're going to sum up to infinity. Okay. There are no infinite disks. All right, but yeah, the potential blows up. That's okay. What happens as x goes to 0? So I'm saying you're moving along x and you're letting it go to 0. What happens to the potential? What? Yeah, excuse me. Goes to a constant, right? That's 0, that's 0. You get sigma 2 pi k r. You get a constant. That's okay. All right. Example. I want to show you.
What shape do we think the universe is?
Right now, or it's like it's pretty flat. Yeah, it's pretty flat. You'd have to talk about flat means something very specific when you're talking about cosmology. The cosmologists today think it's flat, so it's theory of the day. Cosmology, cosmetology, it's sort of the same. They both make stuff up, so I got to erase that from the video. Okay. All right. I'll get a bunch of nasty messages from cosmetology. Well, whoever. Okay. Okay, real quick. Oh, here is a +5 microcoulomb charge. And over here is another +5 microcoulomb charge. And I'm here at some point in between the two. Okay? Midpoint, halfway between the two. What is the electric field at this point? I'm not really worried about the magnitude, the number, okay? The electric field at that point, well, for the charge on the right, there's a field vector this way. I'll call that ER. It's pointing left. For the charge on the left, I'll call that That's an L, by the way. They have equal magnitude and opposite direction. What's the electric field at that point? 0. That's easy. What about V at that point? What about the potential at that point? Well, I'd have to sum it up, but it is not equal to 0, right? Because when you sum it up, you get K5 times over the distance, K5 over the distance. You add it up, it's not going to be equal to 0. So I'm at a point where the electric field is equal to 0, but the potential is not. This has to do with where we defined the 0 potential. With respect to infinity, the potential is not equal to 0. Okay? The electric field at this point is equal to 0. Converse. I'm going to change one of the charges. -5 microcoulomb. Maybe you can already see what's about to happen. +5 microcoulomb at the midpoint. Okay? Which way is the electric field due to the charge on the right? Which way is the electric field due to the charge on the left?
Is there a positive charge in the
Huh?
middle? Is the charge in the middle positive?
There is no charge here. This is a point. This is a point in space. Okay? The electric field at this point is not equal to 0, clearly. What's the potential at that point? V is equal to 0. What I'm getting at is you can have places where you have 0 potential and non-zero electric field.
Would it be
These thi-
0 only if they're at the exact same distance? apart?
Yes. Yeah. Yeah, I'm saying this is the midpoint.
Oh, okay.
Yeah. Okay? Yes.
So it's similar to the relation between potential and kinetic energy? Like when we're
Sure,
talking
yeah,
about gravity.
yeah. Yeah. Okay. Yeah, so let me quickly show you before you leave. Oh, come on. Wake up. Oh, shoot. Trying to hurry. Okay. I knew it. This thing is like when I'm in a hurry, it's not going to behave. Wake up. Come on. All right. Here is a dipole. It's called a dipole. It's a plus charge and a negative charge, and they're close together. The green lines that you see, well, let me talk about the blue first. The blue lines or purple lines, whatever color that is, those are the electric field lines. just like I tried to draw in one of the classes. The green lines are the equipotentials. So these green lines are where, as you move along these lines, you do not change your potential. This is the zero potential. Just like I talked about over there. That's a line where the potential is zero all along that line. If you're moving at a right angle to the field, you're not changing potential. Okay? So these are right angles to the field, and the potential is not changing. But as you move along these equipotentials, the potential is changing. A super simple, the simplest, I think, is there's a positive point charge. The equipotentials are concentric spheres, or shells, spherical shells. I can move along this, never changing my potential, but if I move this or move along here, you're changing the potential, okay? We'll talk more about that. I'll see you next time.